Our guest today is Professor Patryk Mach from Jagiellonian University. Patryk is now heading the Department of General Relativity and Astrophysics, and is also a Deputy Director of the Institute of Theoretical Physics at Jagiellonian University. And as for his young age, he has a lot of achievements already. He did PhD in 2008 in Jagiellonian, and then was a visiting scientist at Max Planck Institute in Garching, and also a visiting professor in Fudan University in Shanghai. And currently, since 1 month, he took over the Polish Society for Relativity leadership. He's our president now. So welcome very warmly, our colleague, and he will tell us today about his numerical simulations, Monte Carlo methods, and general-relativistic Vlasov systems.
Okay, thank you very much for this introduction, and of course, thank you very much for the invitation. A pleasure to be here. I think my last seminar in this institute was much more mathematical than the subject for today, but okay, let's
this will be forgiven.
Thank you. So I will try to tell you something about general relativistic Vlasov systems, and in particular, I would like to advertise a kind of Monte Carlo method that we designed in Krakow, and we designed that method especially having in mind a possibility to get stationary solutions for general relativistic Vlasov systems. So and also I should know that this is a joint work. Adam Cieślik is currently a PhD student in Krakow, but he's going to defend his PhD thesis in December, and he was very much involved in this project, and also a lot has been done by Angela Żwałek, who is also a professor in Krakow. So let me first start with a few words about general relativistic kinetic theory in general, and maybe the way to view this theory in an astrophysical context. So I would say that you could think of general relativistic kinetic theory as an alternative to, or maybe a complementary approach to the hydrodynamical or even magneto-hydrodynamical models. And you would tend to use this approach in those cases where, when collisions between particles of the gas are rare, or equivalently, you could think about the mean free path between individual collisions of gas particles, and you could say that when this mean free path is large, or at least comparable to the length scale in the system, then you might say that probably the local thermodynamical equilibrium would not be established, and then it would be problematic in general to use the hydrodynamical description. Now, kinetic models are usually often obtained by solving the so-called Vlasov equation, and in at least in GR community, referring to the model as the Vlasov model means that we neglect the collisions between particles. If you would like to take into account collisions, then usually you say that you work with a Boltzmann solution in the GR context. Now, this is of course the simplest case, and if you neglect collisions in GR, then you could think of the Vlasov gas as essentially a collection of particles moving freely, and moving freely in GR means moving along geodesic trajectories. And the whole point is that you have to describe this collection of particles moving along geodesics in a statistical way. And this has to be the way in which you can infer from the statistical description some macroscopic quantities that you might be interested in. And in particular, in general relativistic context, what you would like to know from well, your statistical ensemble is, for instance, the energy momentum tensor, and then you could couple this model or this description of matter to Einstein equations. One second. Now, it turns out that in many cases, solutions to the Vlasov equation can be obtained formally. And this, the technique, this type of technique is available when we do have a sufficient control of the phase space geometry of the theory. So when you can say a priori where in the phase space you have the region which is available for the motion and what type of particles can occupy this region, so this and this location and the momenta of a given type, then it turns out that in many cases you can basically solve the Vlasov equation. And what remains to be done usually to get some physical grasp of the situation is to compute usually to compute observable quantities that usually have some form of integrals of the moment. So this would include components of the energy momentum tensor and, for instance, the components of the particle current density. Now, so in this talk, I would like to propose and briefly describe the method that should also deliver solutions to the Vlasov equation in those cases where we do not have this control of the phase space of the theory, and consequently we cannot have analytic or exact solutions. Now, because it is to a large extent a theoretical talk about the construction of this method, and the examples that I'm going to show are intended to persuade you that this is working, I will nevertheless work with situations where actually exact solutions are available. And this is made for purpose. So this will be very simplified solutions, just proving that the technique works. So basically, because you can think of the Vlasov gas as a collection of individual particles that do not collide and that move along geodesic trajectories, the difficulty in this approach, which I will refer to as Monte Carlo, lies in, well, basically two things that one has to do. The first thing you have to do is just to select an appropriate sample of trajectories, and this is actually notoriously difficult part of the problem. And the second problem, which is actually independent of the previous one, is that you have to learn how to do the averaging. So how to take your selection of trajectories and how to average them in order to get the macroscopic quantities you are interested in. So this is basically a kind of coarse-graining scheme that we have to adjust both to the numerical method and to the situation we're interested in. The last problem, which is obvious, namely that you have to compute the solutions of the geodesic motion is I wouldn't say trivial, but the easiest one. You either do this numerically or you solve analytically in cases where this is possible. Now, the examples that I would like to show concern some stationary accretion models, and for simplicity, I will be working only in the Schwarzschild space term. And this is precisely because in those cases we do have exact solutions. And they either exist in the literature or we could derive them for the purpose of this work. But the most important part is that what we are trying to find are stationary solutions. This has a plus. I will, as it will turn out, I will not need any time dependence of the individual trajectories. But also it means that truly a new method is required, because if you take any standard, I don't know, particle inside code, then you will not get a stationary solution unless you know it in the first place. Because usually those methods are adjusted to initial value formulations. You have to put some data and you will evolve them. And those types of systems usually do not relax in a standard way to stationary solutions. So this is a plot from a paper, or actually a collection. This one is from a single paper, I think, published around 2021, that sort of advertise types of advertises the types of solutions that we are interested in. So in this case, we're thinking about a stationary accretion process, a stationary accretion onto a moving black hole. So this is a Schwarzschild black hole that moves through the medium. But because we do neglect self-gravity of the gas, so this is the gas which is just evolving on a fixed Schwarzschild background, we do what is usual in this type of models, namely we sort of select the reference frame associated with the black hole. So we just keep the standard Schwarzschild spacetime as it is, and we boost asymptotic conditions. So instead of thinking about the motion of the black hole through a cloud of gas, I take Schwarzschild spacetime and I say that I'm interested in a solution for describing collisionless fluid in the Schwarzschild spacetime, such that this fluid asymptotically is uniform, has a uniform density, and this gas is boosted in a given direction with a given velocity on the top. And now it turns out that okay, I have to assume something else, something more about this asymptotic boundary condition. And in this case, I also say that asymptotically, this gas is described by Maxwell-Hüttner distribution, which is the relativistic equivalent of the Maxwell distribution. That is, I assume that this gas is in thermal equilibrium, or it's thermal, asymptotic. And this equilibrium is then boosted with a given velocity. And it turns out that this fixes a solution. And it also turns out that I can find this solution exactly. So I can, first of all, I can find the solution to the Vlasov equation formally, and secondly, I can compute macroscopic quantities in terms of just a couple of integrals. Those integrals may be complicated to evaluate at the end numerically, but these are exact formulas. So everything I have to do is compute a collection of integrals. But as you see, the flow pattern that you get is sort of complicated. So you can have some. Actually, the colors here correspond to the logs of the particle number density. So you can basically imagine what happens here. The black hole moves in that direction with respect to the gas, and there is some wake in front of the black hole, and there is some rarefaction region behind it.
And v is the velocity of this black hole?
And v is the velocity of the black hole with respect to the gas at infinity. Mm-hmm. But basically, that's the example of the type of the problem that we consider.
May I ask you a question?
Yes, sure.
So you consider the motion in the collisional gas But before you, collisionless,
Yes.
I understand. So you are the first to consider collisionless gas. And what gas? It was collisional gas that was.
Well,
considered-
I can think about two things immediately. First, I can think that this is just as, you can think about standard gas, I don't know, standard astrophysical plasma.
Mhm.
But in a situation where you think that the collisions are to be neglected.
Now, to me, it was, almost obvious that collision can be neglected. That's why I'm asking.
Oh, well, that depends on the scale, temperature. I would think so, yeah.
And yet collisions are necessary to make temperature sensible.
Of course, so if I refer to any temperature, I would only refer to the temperature at infinity, where I assume by hand that the gas is thermalized. Of course, in the vicinity of the black hole, it makes no sense. Also, the pressures are not isotropic and so on. This is what happens. But another application that I could think immediately about is, for instance, dark matter. Right? So if you imagine collisionless dark matter, then this is the model that should work in principle. Of course, we do not know that. I mean, exactly what that matter is, but you could think about this. I would even prefer the second interpretation to plasma, because for plasma, magnetic fields would be astrophysically essential. So I would have to couple this with electromagnetic fields, which, by the way, is possible in a very elegant fashion, but this is not done.
What is the time of this?
Can I ask the question from the outer world?
Yeah, that's stationary, so it doesn't.
Yes.
It doesn't, yes, but yes, okay.
Łukasz, go ahead.
Yes, that was the question.
Can I ask the question?
Yes, please.
The question is that I understand that you are talking about the Vlasov equation.
Yes.
Vlasov equation is a description of a system which is based on the concept of a self-contained forces. I mean, what is here self-consistently calculated? The interaction between the gas particle, or you have a plenty of of the Schwarzschild black holes, out of which you, I mean, what you describe by what is the concept of a distribution function on that picture?
Okay.
And the other question, since I don't want to confuse the situation even more, why those? What is the meaning of these black arrows on the picture? Are these the velocities of a particle? Then how come that they are not finally all collapsing on this black hole? I mean, if gravitation forces are long range, there is no neutralizing background, so you cannot use the approximation that there is something like a device here or something around the particles, and each of these particles in the gas interact with all others. So the question boils back to the point: what is the distribution Vlasov function in your picture? Thank you.
Exactly. Okay. Very good question. So I will just go into the essential mathematical formalism. Maybe this will make things more clear. But in GR community, people refer to the model which is described in which lives in a phase space, which is described in a statistical way using one particle distribution function. People refer to such a model as the Vlasov model, provided that you neglect the collisions completely.
And the collision of what? And what is the phase space? But this is a distribution of what? Of those light particles or the black holes?
No. Of gas particles. The black hole in the system is.
And then this is not the Vlasov equation, because the Vlasov equation has to contain the self-contained way calculated interaction between those particles. I mean, I'm pretty well familiar with the Vlasov equation. I spent a part of my life solving it.
Yes,
And,
yes, that's
and in a relativistic case and in non-relativistic case, so I am pretty well aware of the Vlasov equation. But if you have a lot of gas particles, then they interact between each other also by the gravity potential. Because if those light particles do not interact by the gravity, then how they can interact with the Schwarzschild black hole? So they have a mass. They have a mass. And there is no speed.
Professor Sulski, maybe we should let the speaker continue and leave the rest of questions to the end.
Okay, but this is a very clear question. So the formulation that I'm using here works as follows. To close the system, to couple the system with the Einstein equation, I would have to compute based on the distribution function, the energy momentum tensor. And then I could plug this energy momentum tensor to Einstein equation. And then have the Vlasov equation, which basically works as an equation for the distribution function. If I consider the two equations, people refer to the system as Vlasov-Einstein. And then, just because I'm interested in this matter sector only, I would like to do what is very often done in working with some matter models in GR. I will neglect Einstein equations. I will simply say that I have a given solution, for instance, corresponding to the black hole spacetime, and then I will be interested in the Vlasov equation in this given spacetime. And of course, the particles can feel the gravity as test particles. So then I have my distribution function that is defined on the phase space, but each particle that I can imagine in the system moves along a geodesic.
So in other words, in the external field.
In the external
That's it.
Exactly.
Vlasov equation works in external field.
Exactly.
Well,
Exactly. Okay.
self-consistent.
So this is
Okay,
not the.
No, I also know.
Never mind.
Vlasov.
The words are arbitrarily used. Yeah. Okay. No question.
Okay. So in GR, this formulation looks as follows. So basically, the phase space is effectively a portion of a tangent bundle to the spacetime manifold or the cotangent bundle. I would prefer to work in a cotangent bundle. So you basically have the locations of particles and momenta. And the distribution function, which is the key concept in this approach, is defined on the portion of this cotangent bundle. Now, for the purpose of this talk, it's essential that I somehow interpret statistically how we understand the distribution function. And the interpretation is as follows. Suppose you have a three-dimensional space-like hypersurface embedded in your spacetime manifold. And suppose that S is the future-directed unit vector that is normal to this hypersurface. And then we say that the average number of particle trajectories in the phase space whose projections on the manifold intersect this hyperset S is given by this formula. So basically, this gives a link to some statistical interpretation. That should be the number of particles essentially contained in a given volume. And to do this covariantly, you have to do this as written here. So eta S is just the volume element which is induced on S, and this thing d vol x is the volume element that is that lives in the momentum space, and it can also be understood as a volume element which is induced. But first, you would have to have an appropriate metric in the cotangent space, which, by the way, you can. So basically, there's a picture. You have this hypersurface. You have those this thing that can be identified as the particle current density vector, and you should count those intersections, and this should give you the number of particles in a given volume. And G mu is that vector. And now, if you would like to couple the system with Einstein equations, this is precisely the question here. You could also define the energy momentum tensor in that way. This is, of course, postulating your model in a sense, right? Because it means that you know how you average out the individual interaction to generate the source for Einstein equations. But because I'm not coupling the system in this talk with Einstein equations, I will not be focusing on T mu mainly. Now, then you can also say that that we all know how to describe the motion of individual particles in a given spacetime. These are, of course, geodesics. You can, for my purpose, it's convenient that I introduce the Hamiltonian description of geodesic equations. So I can associate with a given geodesic this type of Hamiltonian, and the geodesic equations can be cast in this Hamiltonian form.
My question, I ask you, could you explain what a d-wall? Usually, when you do this Vlasov equation, you integrate over the invariant measure, which is not only dp, it's dp dx, which is conserved.
This has this part, and this works as it should.
It's four-dimensional. If you try to use a three-dimensional.
Okay.
But it is, I understand. In Vlasov, you have another special conservation law, and each element in what you call phase space, actually it's not phase space, it's mu space, right? In phase space, you have 1 point, and here you have 6 endpoints, I would say.
No. No, I do have, this is the single particle, one particle phase space.
One particle?
Yes, one particle, yes, okay. And then I have this probability, well, this distribution function on the space space. Yeah.
What is d-wall x p?
This is that.
Ah, yeah, here it is. Okay, I didn't see.
Okay. And so the equation that I will refer to as Vlasov equation basically tells you that this distribution function should be conserved along a geodesic. Okay. And not surprisingly, if you start with the description of your geodesic motion in the Hamiltonian form, then you can write it down as basically the condition that this distribution function Poisson commutes with the Hamiltonian. Now, if you would like to include collisions, then there would be, instead of 0, there would be a collision here, and you would have what people usually refer to as general-relativistic Boltzmann equation. Of course, you can rewrite this equation in a more standard way, and this is something that usually appears in textbooks in GR, usually as a starting point. So in mathematical literature, for instance, people start with this equation and say that that's my field. By the way, there are two very decent introductions which I would like to advertise. The first is a recent one by Olivier Sabach and his students from 2022, and the other one focuses on Einstein-Vlasov systems, where this is coupled to Einstein equation, and this is by Hook and Andreas. And now, so let me briefly start with this idea of Monte Carlo simulation. I would like to approximate my system right now with a collection of geodesics, individual geodesics, associated with individual particles. So basically, I would like to make a transition from a smooth system, which is described by this smooth distribution function, to something that is genuinely discrete. And this is also more or less well known how to do this. Well, at least in special relativistic context, this formula appears in standard textbooks on kinetic theory. And I take this formula as a distribution function associated with a collection of individual particles that move along given trajectories that are described by those functions x mu and p mu. And the only thing that I have to do is I have to make sure that this is written in a proper covariant way. And this looks innocent, but of course here in GR context, it's important that, for instance, these are contravariant components and these are covariant. If I change this, then of course this produces additional terms, which are purely metric terms. And well, the first step in the construction is trying to compute the particle current density associated with the distribution function. So basically, the first observable function that I could have, and I do this in a straightforward way, simply starting from this definition, I integrate over moment. And the result that I get is as follows. As you see, the trouble is that because I started with a discrete system, I still have Dirac delta terms in my description. So because eventually I would like to compare that with something that is smooth. So then we have to do some step, and the step is that I propose that that in a numerical procedure, in order to get something smooth out of this distribution, I will integrate this vector field over or with respect to some small hypersurface, some small hypersurface, three-dimensional, or maybe even less, depending on how I do this, region in space. The trouble here is that, of course, everybody trained in GR would understand that this is not covariant. That it's just the integral of the vector field over some chosen hypersurface. So the excuse is that this is a construction of numerical method, and for me, this hypersurface would have to be a pixel, a numerical cell. It has to be small. Otherwise, of course, this is the and also it's explicitly associated with a given coordinate system dependence. And some justification for this can be done as follows. Maybe I can even skip this. So in a sense, I'm trying to coarse-grain my discrete system and compare it to with the smooth system, but I have to keep all those GR terms under control. And that has to mean that with a growing number of particles, one distribution function has to go to some smooth distribution function. And because these are of distributive type, well, it means that of course they have to tend to each other with respect to some test function, and then by appropriately choosing those test functions, I can show that this type of relation occurs. So basically, that this integral with respect to this hypersurface of this fine-grained J mu goes to this type of integral, and then I could say use the mean value theorem, of course, component-wise, and to take this value in front of the integral and justify this proposition that this should be
average extreme.
Now, of course, then one would need some tests in order to convince oneself that might have a chance of working. And those tests that I would like to discuss here, they are related to stationary accretion problems, as was mentioned in the beginning. So I will start with some models which are, well, maybe not very well known in GR, but that are already known. So for instance, stationary solutions to the Bondi type accretion problem, they are almost exact, and that they have been started in 2017 by Olivier Sabach and Paola De Secco. And you do this as follows. You basically say that the gas, so we do not have a moving black hole, we have a non-moving Schwarzschild black hole. You think that the gas extends to infinity, and asymptotically, we have to put some asymptotic conditions, and these are the asymptotic conditions on the distribution function. And I simply say that, well, first of all, I would like to have a term that basically ensures that I stay on the mass shell, so all particles have the mass m0. And then either I can consider only monoenergetic particles, right, with the given energy, or I can say that the distribution obeys the Maxwell-Eutner distribution at infinity, where it's, well, in the asymptotically flat region, it is well defined. And these are the two examples that I take into account. Now I could also, for simplicity, would work with planar models. So I could say that I might restrict myself to the motion of gas that can, to the gas that can only move in one plane, say an equatorial plane, Schwarzschild space-time. And it has to mean two things as an assumption on F. First, that I'm confined with positions to one plane only, for instance, theta being pi/2, and also that I do not escape from this plane. So I do not add any momentum which would be perpendicular to the plane, because of course I would not stay consistent. And of course that also means that instead of particle current density J nu, I should introduce something like a particle current surface density, appropriately defined, right? Because now everything is defined on the plane. And I will start with this model, this planar model for simplicity. So now, as you see, the key point in this Monte Carlo method is to define this hypersurface sigma. And I can do this as follows. I can take this segment in the Schwarzschild spacetime. So this is the segment which is associated with the standard spherical coordinate system in the Schwarzschild spacetime. So for instance, here I fix the angle phi. These are standard Schwarzschild coordinates. I take a segment between one radius R1 and another one radius R2. Okay, so this is just a segment in the equatorial plane. And then I take, and I say that I'm at the equatorial plane. And then I take a surface, which is the surface because I add time. So I then evolve the segment in time. And then I need to have a numerical cell, which is simply the same as sigma tidal, capital sigma, but with times restricted between T1 and T2. Okay. So there is a picture for this. Okay. So basically this as my segment as is given here. This is a 1, this is a 2. Right? I fix the angle phi, and I have this surface, which is a finite surface. Okay. And in particular, what I can say about this, and which is of course done for purpose, it is also foliated by the orbits of the tiny killing vector associated with this space. And if I do not do this that way, then this construction will not fit to searching for stationary solutions. So this is one of the essential ingredients. So basically, this is the expression. So basically, this construction, this coordinate system of what I choose here has to be adjusted to stationary. And now it's just a matter of a calculation, but it is a straightforward calculation, which you just do by plugging this J mu as it appeared here, to this integral over this surface, to convince one that the result is given by this expression. So what's interesting about this expression? The following thing, it has a sum. It has a sum that runs over all intersections of trajectories with a given hypersurface or given surface. And that's good because, of course, we would think that the individual particles would contribute to my measure of density and so on when they intersect the surface. But also by this calculation, I got another additional terms. So I just learned that, well, this is natural, this is just momentum. But for instance, I got here the weight which is associated with the radius. I got another weight which is associated with the angular momentum, and so on. And this I have to compute every time for a given coordinate. And it's very hard to guess what those weights would be. And another thing that happens here is that in the denominator, I have this time that spans a given surface. Okay, so the time from T1 to T2. And of course, normally I do not want to know what the time is. But also, I would like to say that I'm interested in stationary solutions, so that also the entire system is invariant with respect to translations, with respect to the time. And I can replace this difference of time simply by a normalization, by the number of particles that I can put into my calculation. So this is how it works. And now the trouble that arises here is, of course, that this is fine, provided it works. But we would have to know how we would like to select appropriate distribution of geodesics. And the point is that this construction is fairly general. It knows nothing about the system that I would like to investigate. But the system is fixed by the fact that I have assumed some asymptotic conditions. So if I would like to have a system that, or a solution that corresponds to those asymptotic conditions, now I have to select my trajectories, my geodesics, appropriately. So from this distribution. And this is usually the most difficult part. Because usually when you write things like that, those expressions are not well adjusted to the way in which you really describe the geodesics of this individual trajectory. And you really have to know how many you really have to construct a sample. But actually, okay. And also, what you have to do is you have to eventually put this onto the computer. So you do not really consider trajectories that reach infinity. You may consider them analytically, but you have to restrict yourself to some finite region. And now it turns out that for instance, this problem of the planar accretion immediately finds a connection to something that is known in mathematics, in elementary mathematics, as Bertrand's paradox. So let me remind you from high school what that was. So Bertrand's paradox is usually formulated as follows. You fix a circle, and you randomly select a chord on the circle. And then you ask the question, what is the probability that the length of this chord is larger than the side of an equilateral triangle that you inscribed in the circle? And back then, in 19th century, people were worried by the fact that they find very different solutions to this problem and very different answers, depending on the way in which they realize this work. This phrase randomly select, the measurements. Now, how that is related, maybe I can show immediately the picture. Because I know that at infinity, the gas that I would like to describe has to be a uniform distribution of particles moving randomly in any direction they would like to move. And my asymptotic conditions are specified precisely at infinity. So my distribution function should somehow resemble this type of randomly distributed collection of trajectories. And then I could basically say that, okay, I would take for instance, the geodesic parameters that are associated with such, well, asymptotically, geodesics are just straight lines. Asymptotically, the Schwarzschild spacetime is the case of the Minkowski spacetime. So, of course, every particle more or less moves along a straight line. And I can take so basically my problem is that I should take the distribution of geodesic parameters from such a picture and translate it to the parameters that would work also for the Schwarzschild space. And this is actually almost trivial, because many of those parameters can be selected as constants of motion. So it would work. For instance, the angular momentum can work. But selecting those parameters, I have to know that I fit to the right asymptotic condition. And also, I have to do this selection on a fixed portion of my numerical grid or my numerical problem. And this is precisely where the Bertrand paradox ends. Because for right now, my selection should be one of the realizations of the Bertrand paradox. So I basically have to think about the way in which I would like to select trajectories, for instance, straight lines on a circle, because the selection is first thought of as done asymptotically at infinity. Now, actually, when you think about selecting such trajectories, you also know something more. You know that you are only artificially confined to the circle. So I will speed up. And that means that your distribution should rather correspond to a uniform distribution of lines on the plane. And actually, it's well known how to define such a distribution. Those types of things were studied already in '63 in Kendall and Moran, for instance. And then you can learn that the solution that gives you the distribution function that is invariant with respect to, say, Euclidean symmetries, translations and rotations in the plane, is given by that expression, but this one works in Cartesian form. So then what you can do, you can translate this into some polar coordinates, where P is the distance of the given chord from the center of your coordinate system, and And then this is the distribution. So you basically know that F is 1 over P. And this solution was actually known already to Poincaré in 1912. So this is what he has in his discussion of Bertrand's paradox. Now, in our case, this translates immediately to angular momentum, because on the plane, the angular momentum of the trajectory is just proportional to this p, this closest distance in which each approaches the center of the coordinate system. And this is precisely the distribution that you would get on the plane with this solution. And this is precisely what you would get for the problem at hand. So these are trajectories in Schwarzschild, where you apply this type of distribution over angular momenta asymptotic. Okay, so that's basically what we are searching. And now the point is to take this type of sample of geodesics and do this averaging. And basically, this is what I do. These are some technical issues related to the fact that a given trajectory might intersect a given segment many times, and I also have to take this into account. And if I do all this, basically the result is as follows. Okay, so that's the solution, and the solid lines are obtained by an exact solution of this problem. This is actually done for monoenergetic particles. And those scatters points, these are the results of those averages. And of course, I exaggerate here, so I take the number of particles which is small enough so that you can see anything on this plot. So this is how it works in planet symmetry. I will probably skip the discussion of what happens when you work for three-dimensional models. The main message is that those distributions of the momenta matter. And in 3D, or the angular momentum, that this matters. And in 3D, this distribution is different, simply because the uniform distribution of straight lines in three-dimensional space is different than the uniform distribution of straight lines on a plane. And this is what we have to take into account when assuming the asymptotic boundary. But again, if you know this, if you do this lesson, then the agreement is just perfect. But and of course the solution is different. So this is the solution for the same problem, but where the gas is not confined to the equatorial plane, but where it can flow from any direction spherically, in a spherically symmetric way. So maybe as a last part, I would like to advertise that you can also go beyond this axial symmetry for a planar model or spherical symmetry for a 3D model. And what I consider here is something very, very similar to those boosted black holes at the beginning. But for simplicity, we show the result for a planar model. So this is sort of artificial. You consider the gas that can only move within a given plane. And then you have a black hole which only moves in a given plane, in the same plane. And everything else is as it was. So asymptotically, this gas is described by the boosted Maxwell-Newton distribution, and in spherical or cylindrical coordinates, this asymptotic distribution has to have this form. So this tells you that you do not escape from one given plane. This tells you that you are on the mass shell. And this is this boosted Maxwell-Newton part. Epsilon is related to the energy of the particle. It's actually a normalized energy. Gamma is the Lorentz factor. Which is associated with the boost velocity. Pi is the angle, because this of course breaks the symmetry. And epsilon r is just a sign which tells whether you are going inward or out. So let me now first show the result, and then maybe comment on some troubles. So this, on the left panel, is the exact solution that you can compute. I'm not showing how you can do this, but basically you can solve exactly the Vlasov equation that we have seen for those asymptotic conditions, and this is done on the left. And here there is a simulation that Adam Cieślik was able to do and compute with quite a huge number of particle trajectories, where he basically repeats the same procedure for an appropriate selection of trajectories. And it works, and you can also see that, of course, on those types of plots, it's hard to say what the error is and whether this is even the same. But you can have some two-dimensional plots where you, for instance, focus on just one component of this particle current density or surface density, and you look at those components at given radius, and this fits that's here. So what's the main difficulty with those type of problems here? Well, the main difficulty is that now you have to select trajectories from such a distribution function, asymptotic. And now imagine what that means. I have a trajectory that starts somewhere on my boundary. And imagine that it's not a trajectory that ends in the black hole, so not a particle that falls into the black hole, but a particle that is scattered by it. Right? You go near to the black hole, you do some revolutions, and then you have your angular momentum, which is high enough, and this particle goes to infinity. Right? So then it means that if I select this particle and it ends up somewhere else, once again, at infinity, it would contribute to this, to my budget. So this selection would have to somehow take this into account. And this is of course numerically very difficult, because there would be some conditional probability that we can compute. So we don't do that. And the trick we do is as follows. We divide those trajectories in half. From infinity to the pericenter, and another half from the pericenter to infinity, or to the outer boundary. And then we select those two halves independently from this distribution. And fortunately that works and it saves the problem. So I can have those stationary solutions. So I think I should summarize. So let me summarize. So I believe that this is the model and the method that should eventually work, and that should deliver solutions for stationary problems. Also in those cases where I cannot compute exact solutions. Of course, here I could, but I imagine that I'm trying to tackle the problem on, say, Kerr metric, and this is already fairly complicated at this point. So I would like a good working method, which would give me stationary solutions. And this is, as you see, threefold. The first step is, of course, that you have to be able to compute particle trajectories in a given spacetime in an efficient way. The second problem is that I have to be able to, and this is the most challenging one, I have to be able to select parameters of trajectories that correspond to my required conditions, either initial conditions or boundary conditions. So basically something that I want to compute. And of course, I have to then count basically intersections of trajectories with some time-like surfaces, but I have to know the weights. And this is the easiest part, because there is a way of computing this for a given grid. This might be, of course, problematic. Now, I have to say that it's essential to understand that those things are disconnected. But there is some plus. For instance, I can select my trajectories in a very, very wrong way, not corresponding to the asymptotic state, asymptotic, or any condition that I would like to impose on the system. It will still be a correct solution to the Vlasov equation, because I started with the correct method at the beginning. All trajectories are really properly computed geodesic trajectories, and everything else is just this averaging of coarse-graining technique. But of course, usually this is not what one searches for. Usually one wants to have the control about the solution. Now, what will be the outlook? The outlook, of course, more complicated flows, even on Schwarzschild spacetime. And well, my personal motivation was to go to CARE in those cases where I cannot do this analytically. But there are other things that you could learn, and probably you would like to test on this Monte Carlo scheme. For instance, the calculation concerning the dynamical friction that this black hole feels when moving through the medium. This is sort of conceptually problematic in this type of models, and then you should be able, in principle, to have some expressions associated with individual particle systems. Another question is, can we include electromagnetic fields in this model? In general, this type of kinetic theory has a nice coupling with electromagnetic fields within GR, but of course the implementation has. So let me stop here at this moment.
Let me allow for a couple questions, maybe you and other also people who didn't ask so far. So please.
So can you explain, the Monte Carlo means averaging, and you choose your boundary condition, then you choose correct trajectories corresponding to this solution, and then it goes through the Maxwell Hamiltonian equation. You know all the trajectories, and then you have to average over this surface, right?
Yeah.
So what is the weight? You average only once at the very end.
No. Weight is for a lack of a better term. Weight means that if I, for instance, would like to average momenta, right, to compute the J mu, I would naively understand that I have to take the momenta associated with individual trajectories, and count the trajectories that really intersect my numerical stuff. But it turns out that I have to multiply this expression.
What do you mean it turns out? It's mathematically proved, or?
Yes, mathematically proved. I take this integral as defining my method, and then
okay, so it's a formula for the correct formula for averaging. That's it.
Yes, you could say this. Yes.
But you averaging only once at the end, right? When all trajectories are known.
Yes.
So that's somewhere on Monte Carlo is all the time averaging.
Well,
that's why
yes, I agree.
You know,
I agree. So the point is, what would be the term for this type of approach?
I know how the Vlasov equation is used to be solved, numerically. There is a method of hard particles. They move into more or less with the same volume. Yes. And I said, so that's one way. But you don't have this at all.
No,
it's completely different.
Yes, I want to avoid.
Yeah, okay, that's very good. Because I don't like.
No. You can discuss over the content. Mikołaj, you want to start.
I think that the big advantage of this method is that you get rid of time in practice, and you basically work with trajectories and sort of time disappears.
Yes, this is
But
how.
here I have one small problem, namely, in practice, you have to introduce this type of temporal cutoff.
Yes.
However, in practice, there might exist trajectories which wind around the black hole as many times as you want.
Yes.
And you may fail to capture them, to cut the integral too short. They're probably extremely rare, because they would have to be adjusted very clearly, but it is possible that your trajectory just winds around the black hole as many times as you want.
You're right.
But since this, I think that they tend to be very rare.
This is they are rare, but they are present. So, for instance, this is an example of such a trajectory, right? Well, here the reason of including this example was just to emphasize that these are not integrals of the those sums do not go over trajectories. Actually, they go over intersections with cells. So one trajectory can contribute many times to a given cell, right? If it winds up in such a way. But the point is that the way you get rid of this cutoff is precisely by assuming that you are searching for a stationary solution. And if so, then I can in fact get rid of this normalization by introducing a normalization by the number of trajectories that I have included in my sum. And
Don't you lose total normalization of this J this way somehow?
well, the problem is that that in principle, for those models that actually extend into infinity, there is a three-parameter, which is this normalization of the J, right? Because you do not have a fixed number of particles in the full system. Usually that can be fixed by specifying asymptotic density.
Yeah, that's how you recover it differently values you get.
Yes. But I can recover this, still retaining control over this function, just by comparing this time and the number of trajectories.
And second short question, did you consider what happens if the velocity of this black hole goes to the speed of light? If this is a very fast black hole.
Yes and no. So yes, in the sense that when trying to get those solutions exactly, sometimes we have to compute some integrals, and they are of course problematic in this limit. But of course we could go to large values.
Okay, so now I have also a question, maybe it is very different from all the others, but that would be much easier. So can you give one specific example of astrophysical application of this problem? Even if you take into account the electromagnetic field and Kerr black hole, what kind of situation you can imagine to test your model and somehow compare to observables? Is it possible?
Well, I don't think that we have right now any observation of black holes that are really moving in a sort of stationary way through the system. You have this implicitly. So, for instance, what you should have, you do have this binary black hole system where OJ something.
Yeah, I know.
Right? And then there is the companion black hole that from time to time pierces the disk, which has some density. And this is, well, of course, it's disputable what we really observe, but I think the consensus and the standard explanation is that the variability that one can see in radio and in optical regime is precisely due to this piercing and
yeah, but variability could be in the radio from the jet, right?
Yes,
One of these black holes.
yes, of course. So this is what you do not know, right? So this is one system where you have the black hole moving through the medium.
Through the medium.
And you could say, well, this is absurd. Right?
Yeah, could this produce a jet, for instance, this kind of motion if this black hole is moving with the speed of light almost.
Uh,
Yeah, must be because I've heard of some speculations actually.
Yeah, but I would say, well, observationally, these are things still
It could
speculate.
be a jet mechanism, like motion of the black hole through the medium rather than.
Now, I mentioned this drag mechanism. Drag is interesting because you could think that that it could have the long-term implication. Right? Even in a wide binary system, this could be a mechanism of well, making a wide binary system a compact binary system, right? So this is related to this problem, which is sometimes referred to as the final passing problem. How to get rid of, how to produce compact systems of consisting of massive black holes. But then, of course, you would have to assume something about the matter in order to get the number. Right? This could be only understood either indirect measurements.
Okay, are there any other questions here or on Zoom?